In this video, we will review all of the types of hypothesis testing that we've covered. We've covered one sample mean with the t-test, one sample proportion, two sample independent means, two sample dependent means, two sample independent proportions, and the chi-square goodness of fit test. Here's our summary of the three ways to perform hypothesis testing. In the classical approach, we need two pieces of information. We need a test statistic and we need a critical value. The critical value tells you the area of the shaded region, where that value starts. So for a two-tailed test, your critical values, you have part on the left and part on the right. And if your test statistic falls in either of these two regions, then we reject the null hypothesis. If we have a left-tailed test, alpha, our significance level, is only on the left-hand side, and our critical value would be here. If our test statistic is smaller than this critical value, then we will reject. In our right-tailed test, alpha is on the right-hand side, and our critical value is here. And if our test statistic is greater than our critical value, then we will reject. If we're doing hypothesis testing with the p-value approach, the only thing we need to remember is that if the p-value is less than alpha, our significance level, then we reject. If we're performing a confidence interval on a one-sample, two-tailed test, and once again, this is a two-tailed test, alpha is split over the two sides, then we reject the null hypothesis if our parameter, either the mean or the proportion, is not inside of our interval. If we're doing the confidence interval approach for a two-sample, we reject the null hypothesis if 0 is not within our interval. So here's our hypothesis testing overview for the three types of hypothesis testing that we have been performed. Your critical value for all means, the function that you use in your calculator to find it is inverse t. When you're dealing with proportions, in order to find your critical value, you use inverse norm. And for chi-square, if you have a one-sample mean problem, in order to find your p-value and your test statistic, use the t-test. If you have two samples with independent means, then you use two-sample t-test. If you have a two-sample dependent difference, for one sample proportion, you use one prop z test. Two sample proportion, you use two prop z test. If we're calculating confidence interval, for a one sample mean, we use two in t interval. And this is only if we have two-tailed tests. If you're working with two sample independent means to find your confidence interval, you use two samp t int. If you have a two-sample dependent mean, we use t-interval on L3. So just like one sample mean, we're using t-interval. If you have one sample proportion, we use one prop z int only if it's a two-tailed test. If it's a two-sample proportion and we want the confidence interval, we use two prop z int. And what you should notice is confidence interval, they all have interval or int in the title. If you're doing hypothesis testing for the p-value approach, they all have test in the name. Our null hypothesis is listed for each of our different tests. If it's a one-sample mean, your null hypothesis is always that it's equal to a number that was given in the past. Two-sample independent means, the mean of sample 1 is equal to the mean of sample 2. For proportions, the population proportion is equal to a certain number, and two sample proportions, the proportions of the two samples are equal to one another. Here we have our alternative hypothesis. If you replace the equal signs from the null, it can be any of these tests. Not equal to means it's a two-tailed test. Less than, less sign means that's a left-tailed test. Greater than is a right-tailed test. So when we are interpreting our results, if we decide to reject the null hypothesis, then we can state our conclusion in any of these three ways. If we fail to reject our null hypothesis, we can state our conclusion in any of these ways. So where you can find all of these features in your calculator, if you press Stat and move over twice to Test, you will find all of the tests and all of the confidence intervals that you need. If you're defining the critical values, use seconds and vars, and that will take you to distributions. And here you would have inverse norm, here you would have inverse t. So tips for how to approach any of these hypothesis test problems. Make sure that you read the problem slowly. Identify the parameter in the problem. Is this a mean problem or is this a proportion problem? Proportions have percentages, or they ask a question in such a way that it is a binomial experiment. So you ask a question where the only answers are agree or disagree, pass or fail, right or wrong. There are only two mutually exclusive options for proportions. Identify whether you have one sample or two, then perform your corresponding analysis. So here's our first problem. And you can always pause this video so that you can take your time to read it and see if you can perform the test. So here we want to know, do we have enough evidence to say that LA doctors work significantly less than the rest of California? So our null hypothesis here is that our mean is equal to 60. Your null hypothesis is always a given statement from the past or history that we assume to be true. So if the California average is 60 hours a week, that's the null hypothesis. That's the initial statement we're going with. Our alternative hypothesis, does the given evidence state that LA doctors work significantly less? So this is a left tail test, and the numbers are always the same, 60 and 60. So if we're doing the p-value approach, we have one sample mean. We're going to use the t-test, and mu sub 0 always comes from the null hypothesis. X bar is our sample mean. So from a random sample of 49 doctors, in our sample, they worked 53.1 hours with a standard deviation of 7.2. We select left tail test, and here are our results. So here is our p-value, and make sure you pay attention to that whole number. So E is scientific notation, which means this number times 10 to the negative 8th power. So since our p-value, which is basically 0.000, round to 3 decimal places, since that's less than alpha, we reject null hypothesis. If we did this using the classical approach, we find our critical value using inverse t. We find our test statistic using our previous test. Here's our test statistic on that top line, negative 6.71. And we compare our results. So here is our critical value at negative 1.68. If we plot our test statistic on this graph, we would see that it's in this shaded region. It's in the unusual area. So since it falls within the critical region, we reject the null hypothesis. Another way you can say it is we reject the null hypothesis because the test statistic is less than the critical value. So we're doing this two different ways, but our results should always be the same. Here we have two training programs. So since we have two training programs and we're looking at means, this is a two sample mean, and this is an independent problem because the dogs in program A have nothing to do with the dogs in program B. There's no ties between the dogs individually. So p-value approach, we want to sample t-tests. We enter in all the results for the first sample, enter in all our results for the second sample. This is a left tail test because we want to know, was the training for program A significantly less than program B? You always leave pooled on no. And here are our results. This is our test statistic. Right below it is our p-value. Since our p-value is less than alpha, we reject the null hypothesis. There's enough evidence to say the length of program A is shorter. If we do this with the classical approach, we find our critical value using inverse t. Inverse t takes our area to the left, and since this is a left-tailed test, the area to the left is alpha 0.01. When you have two samples, the way you find your degrees of freedom is you take your two sample sizes, and whichever one is smaller, you subtract 1 from it. So our sample size here is 40. So our critical value is negative 2.423. When we found our test statistic from the previous screen, our test statistic was negative 2.7. So when we plot that, since it falls within the critical region, the shaded area, we reject the null hypothesis. There is sufficient evidence to say that the mean length of time for program 1 is smaller than the mean length of time for program 2. Here, we have a right tail test, and the wording of the problem, you had to pay attention to this one. Initially, you would think that since it's dropped, it would be less than, but you have to read the problem. So in 1975, this was our first sample. In 1991, here's our second sample. So if over time, the proportion of U.S. adults who strongly agree with the statement has dropped, that means that in 1975, this number is larger than the value we received in 1991. So that's why it's a right tail test. So p-value approach, we use 2-prob-z test. Enter in our first sample and our second sample. Right tail test. Here is our p-value. Remember, E is scientific notation. So this is 7.21 times 10 to the negative 9th power, which is essentially 0. So since our p-value is less than alpha, we reject the null hypothesis. There is sufficient evidence to say that the proportion of adults in 1975 who believe people should take care of themselves is greater than that in 1991. If we do the classical approach, we find our critical value using inverse norm, because this is a proportion problem, and proportion problems always use inverse norm. Inverse norm takes area to the left. So since this is a right tail test, that means 5% of our data is on the right. And inverse norm takes area to the left, so everything that's on the left would be 1 minus 0.05, so 0.95. Standard normal distribution, mean is 0, standard deviation is 1. So our critical value is 1.64. And our test statistic that we got from our 2-prob-z test is 5.67. When we plot that point, it's far to the right. And since it's within our critical region, it's in the shaded area, then we reject our null hypothesis. Alternative hypothesis, we wanted to know, has the attitude changed? 1-prob-z test, there's only one proportion here. They only took one sample, and that one sample was in 1995. And P sub 0 comes from the null hypothesis. This is what we previously knew, what had already been accepted, and the information that we are basing everything off of. We enter X, the number of people with a certain characteristic. N is always our sample size. We have a 2-tailed test. Here is our test statistic. Here is our p-value. Since our p-value is not less than alpha, we fail to reject the null hypothesis. So there's insufficient evidence to say the attitude has changed. If we're doing the classical approach, we find our critical value using inverse norm, because this is a proportion problem. And with 2-tailed tests, when you're trying to find your critical value, you take alpha and you divide it by 2, because alpha is both of these tails together. So we just want this value. And we have our negative 1.64 as our negative critical value. But since this is a 2-tailed test, you have another side as well. And since they're symmetric, we know the positive value, 1.64, is the other critical value. Our test statistic, 0.5, since it does not fall within those critical regions, we fail to reject the null hypothesis. confidence interval approach, we use 1 prop z int. C level, make sure you're paying attention to alpha. So alpha is 0.1. So when we add the C levels together, that should give us. And here's our confidence interval. Since our confidence interval does not, we fail to reject the null hypothesis.